Why is calibrating autonomous robotics navigation systems so complex? Imagine trying to get a robot to walk through a busy city street without bumping into anything or getting lost. It sounds simple, but behind the scenes, it's a huge challenge. When robots move around on their own, they're relying on many sensors to see, hear, and feel their environment. These sensors include Lidar, which measures distances with laser beams, cameras that capture images, inertial measurement units that track movement, and wheel encoders that count how far the robot has traveled. To work well together, all these sensors need to be perfectly calibrated so their data lines up accurately. Even tiny errors can cause big problems, like crashing into obstacles or losing track of where they are. Calibrating these sensors is tricky because each one works differently. Lidar can give very precise distance info but struggles with shiny or see-through surfaces. Cameras are affected by lighting, shadows, and weather. Inertial measurement units can drift over time, giving false readings. Wheel encoders might slip on uneven ground. Combining all this noisy data into a clear picture of the surroundings takes careful tuning. Robots also face changing environments. They might go from smooth floors to rough terrain or crowded streets filled with moving people and vehicles. Calibration must adapt to these shifts so the robot can still find its way accurately. This means constantly updating sensor settings and algorithms to handle new obstacles or lighting conditions. Processing power is another hurdle. Robots have limited onboard computers, so they need to make quick decisions. Calibration parameters must support fast calculations without sacrificing accuracy. If the system is too slow or imprecise, the robot could make wrong moves or stop altogether. Different types of robots add more layers of complexity. A wheeled robot moves differently than a flying drone or a legged robot. Each shape and mode of movement affects how sensors perceive motion and surroundings. Calibration must consider these physical differences to keep navigation smooth. In human environments, robots also need to understand social cues. They must navigate around people politely, respecting personal space and social norms. This requires calibration of systems that interpret human behavior, adding another challenge. Navigation involves many parts working together, knowing where the robot is, creating maps of the environment, planning routes, and controlling movement. Each part needs precise calibration, and all must work seamlessly. If one sensor or algorithm is off, it can throw off the whole system. Think about delivery robots on sidewalks. They need to avoid pedestrians, handle curbs, and deal with unpredictable movement. Autonomous cars must interpret traffic signals, other vehicles, and road conditions at high speeds. All these tasks demand extremely accurate calibration to keep everyone safe. So, the process of calibrating autonomous navigation systems is complex because it involves aligning different sensors, adapting to ever-changing environments, making quick decisions with limited computing power, and understanding physical and social factors. It's a continuous process of fine-tuning, testing, and updating to ensure these systems operate safely and reliably in the real world.